Welcome to Lecture 2, Butterflies, Glaciers, and Hurricanes. In the first lecture, we looked at the temperature trends over the last 150 years, and we found that the Earth has been, in fact, warming. We found that warming wasn't even, that things were roughly steady in the late 19th century, that there was a warming trend in the early 20th century, a roughly even trend in the middle 20th century, and then a much more rapid warming into the 21st century from the last few decades of the 20th century. That's perhaps the clearest indication that Earth's climate is changing, but climate is about a lot of things other than simply temperature. It's about humidity, it's about moisture content of the soils, it's about cloudiness, it's about precipitation trends, it's about a lot of other aspects of the state of the atmosphere. Furthermore, there are other indicators that can tell us about changing climate that are independent of the measured surface temperatures that we talked about in the first lecture. And in Lecture 2 here, we want to look at some of those other phenomena that may indicate that Earth's climate is also changing. Some of them themselves will be simply other ways of measuring temperature, but some will be entirely different phenomena. Phenomena involving animal and plant species, phenomena involving storm intensities, phenomena involving ice, that also indicate that Earth's climate is changing. We'll be looking at all of those. Scientists call some of these phenomena that are indicative of climate change fingerprints. They use the word fingerprints of climate change, and they use the word fingerprint in a particular way. Some of these changes that we are seeing, other than the thermometer temperature changes I discussed in the first lecture, some of these changes are themselves things that we would expect to have happen if climate change were occurring in a particular way for a particular reason. In particular, some of the changes we're observing today are changes we would expect as a result of anthropogenic, and that's the word I'm going to use again and again in this course. Anthropogenic means of human origin, anthropo, human. Some of the changes that we see are, quote, fingerprints of anthropogenic climate change and give additional evidence to the statement I made in the first lecture and the statement that I'll elaborate on in the second half of the course, that at least some of the climate change that we've seen in recent decades is caused by human beings. So what are some of these fingerprints? What are some of these other indicators of climate change other than simply taking the global temperature with thermometers? Well, that global temperature record, remember, was surface temperatures. It was made from thermometers mounted about the height of my eyes above the Earth's surface, so it's basically the surface layer of air. It was made from thermometers that measured marine air temperatures, temperatures just above the sea surface, and it was made from sea surface temperatures, SSTs, temperatures of the surface waters of the ocean. So it's temperatures at the surface layer of the Earth. But there are other temperatures you can measure that also say something about climate change. For example, if you dig a hole down into the Earth, you'll find the temperature changes with depth. How should it change with depth? Well, if you think about it, the interior of the Earth is very hot. It's thousands of degrees. There's a molten outer core of the Earth made largely of molten iron. Things are hot down there. That's the primeval heat that the Earth comes with. Some of it is still left over from the formation of the planet, and some of it comes from the decay of radioactive elements inside the Earth. I'll say more about that when we talk about energy sources, because that is one of the energy sources available to us. But if things at the surface were completely steady, if we had a steady climate at the surface, what we would expect to see if we drill down into the Earth is an increase in temperature. It's not a very dramatic increase, but we would expect to see a measurable and, more importantly, steady rise in temperature as we went down into the Earth. Now, what happens if the planet's surface is warming is that additional heat flows into the Earth from above, instead of just flowing to the surface from below. And when that happens, the temperature profile that we would expect to measure if we drill down into the Earth would give us warmer temperatures in the surface layers of the Earth than we expected, and we would have to drill down some significant distance before we began to see that steady increase associated with the geothermal heat in the Earth's interior. So that's a long-winded explanation of what's called borehole temperature measurements. A borehole is simply a hole bored into the Earth, and we have lots of them. Because every time we've bored for oil, we've made a borehole. There are abandoned oil wells and mine shafts and all kinds of other boreholes around the world. And if you study the temperature profiles in those, you're learning something about what's been happening to surface temperatures over timescales of decades to centuries, typically. Why is that again? It's because the surface temperature signal, if I can call it that, slowly propagates into the ground and leaves us a kind of record with depth of what the temperature has been doing. And until we get to that depth where the geothermal heat flow begins to dominate, the outer layers of the Earth's surface are dominated by these effects of recent climate change, and we can read that climate change by measuring temperatures in boreholes. So that's one way of getting at temperature change over the last decades to centuries. Furthermore, those borehole temperatures are interesting because they smooth out fluctuations as the heat gradually diffuses into the Earth. Fluctuations, for instance, a particularly warm year or a particularly cool year, those will be smoothed out, and we'll get a kind of average sense of what the climate has been doing over the years. So what do the borehole temperature records tell us? Well, they tell us simply that the Earth has indeed been warming. Now, we don't have enough borehole temperature measurements to get a really clear global picture, but just about everywhere we've looked at borehole temperature profiles, the results are consistent with the surface temperature profiles I showed you for the 150-year temperature record. So boreholes provide a kind of smooth averaging that gives us a sense of what's been going on kind of a time scale of decades or so. So that's one example. And a very recent study, by the way, suggests that the upper surfaces of the continents have absorbed an enormous amount of energy because of this heat flow from the warming climate. And so there's a big reservoir of energy, and that may in turn begin to have its own effect on climate. The land area, the land and the rocks absorb this heat, and they can release that heat if they need to under certain conditions. Another place where a lot of heat gets stored is in the upper layers of the ocean. Again, there are temperature profiles associated with the ocean in its natural state, and as the surface begins to warm, some of that warming permeates down into the oceans, and it changes the temperature structure of the oceans. And from that, we can calculate what's called the heat content of the upper layers of the ocean. And that's a measure not of what the climate is doing right now, but what it's done over time, how much heat has accumulated in the surface layers of the ocean. And that trend also shows an upward rise in temperature. So the surface temperatures of the ocean have been rising, the temperatures in the top layer, the extent to which warm water goes downward into the ocean has been increasing, and there's an increase in the heat content of the upper layers of the ocean in the past few decades. Finally, there's the atmosphere. The surface temperatures I talked about in Lecture 1 are measured, again, largely just a little bit above the surface, or in the case of sea surface temperatures, in the upper layers of the water. They're not measured high in the atmosphere. What have those temperatures been doing? Well, there's been a lot of discussion of that over the past few decades, and only in recent years has it become pretty clear what's happening there. In fact, if one looks in the lower atmosphere, the so-called troposphere, the lowest layer of the atmosphere that extends upward, to a little bit higher than commercial jetliners fly, up to maybe 8 or 9 miles above the surface, 10 kilometers, varies quite substantially, but that's the lowest layer of the atmosphere. That's the layer in which most weather occurs. And temperatures in the troposphere, in fact, show a warming. Those temperatures are not easy to measure. The old way of measuring them was to send up weather balloons, so-called radiosondes, equipped with suites of instruments that would then radio their results back. And of course, you were only probing a small part of the atmosphere and only in a certain time. And those data are not terribly consistent. They're difficult to build a global picture of the tropospheric temperatures. In recent years, we have instruments called microwave sounding units that are flown on satellites. They look down on the atmosphere, and they can calculate a rough average temperature for vast volumes of atmosphere based on microwave emission from oxygen molecules in the atmosphere. They're also a little bit hard to interpret because they can tend to smear out the temperatures in different layers of the atmosphere. And there's been a lot of discussion of what those temperatures have been doing. But in recent years, it's become clear that the troposphere has also showed a warming of approximately the same magnitude as the warming at the surface. Some of the latest measurements suggest the troposphere has, in fact, warmed a little bit more than the surface. And if you looked at a graph of that, you would see a warming trend for the surface, a slightly larger trend for the troposphere. Now, above the troposphere is the next layer of the atmosphere, the stratosphere. And in the stratosphere, things happen rather differently. The stratosphere shows a marked cooling. And if you looked at a graph of the tropospheric and surface temperatures, and they showed an upward trend over the past few decades, the stratosphere would show a sharp downward trend. In fact, a more substantial downward trend. You may, wait a minute, how can I say the Earth is warming if the stratosphere has been cooling? Well, as I'm going to show you in lectures 4 and 5, on the basis of the science of how climate is established,